Changes in the spread of a process can lead to out-of-specification products. In this lesson, you will learn how to create a standard deviation control chart to monitor the process spread. And hello again to this lesson, which essentially has three learning objectives. First, you should be familiar with the terms standard deviation and precision, and understand why the standard deviation should be monitored as a measure of the spread of a process. You should also be able to use a sample to calculate its standard deviation. And of course, the focus of this lesson is that you should be able to create a control chart yourself and calculate the warning and control limits. This lesson is divided into 3 chapters. In the first chapter, you get an overview of what the standard deviation is and how a change in the variability can lead to characteristics that are out of specification. In the second chapter, the standard deviation of the process is calculated based on the data from a pre-series. And in the last chapter, the actual control chart is created and the warning and control limits are calculated. To be able to classify the standard deviation control chart in comparison to the other quality control charts, this picture shows the connection between the various characteristics and the control charts used. The different characteristics are shown on the left and the different control charts on the right. The quantitative characteristics, shown on the left, can be divided into 2 different categories. First, the variable characteristics. These are all characteristics that can be measured. They always have a value and a unit. Examples of this would be the length, hardness, weight, surface roughness, or tensile strength of a component. Second, there are the attributive characteristics. Those are all characteristics one can only count. But we don't want to go into detail about them here. On the right, we have the different control charts for variable characteristics with a white background. These are also called Shewhart charts, named after American Walter Andrew Shewhart. As you can see, there are 3 control charts for monitoring the process location and 2 control charts for monitoring the spread. The standard deviation chart is one of the spread charts. Let's start with the basics of the standard deviation and why it should be monitored. As a practical example, we take this tried and tested piston again. The product characteristic to be monitored is the nominal diameter of 60.1 mm. The standard deviation was already discussed in detail in one of the basic lessons. Therefore, only the essential is repeated here. Without going into more detail about the exact calculation, the standard deviation is simply a measure of the spread of the values. Its unit is the same as that of the monitored product characteristic. Product characteristics that are the result of a process that is subject to random variation can, for example, be randomly distributed as shown here. This Gaussian bell curve has its inflection points at 1 time the standard deviation. To describe the precision, one can, for example, determine the standard deviation of a process result. This can be calculated, for example, with the MS Excel function stdev.s. A small standard deviation corresponds to a small spread of the values, and a large standard deviation corresponds to a large spread of the values. As can be seen on the right, an increase in spread can result in the lower and/or upper specification limit being exceeded. These would be the measured values shown here in yellow. Monitoring the variance using the standard deviation makes more sense with larger sample sizes. With smaller sample sizes, it is more likely to monitor the range using a range chart. The distributions just shown in the diagrams are based on concrete individual measured values. These individual measured values are shown in this value curve of a control chart. It can also clearly be seen how the values in the first part vary only slightly around an average value and are far from the specification limits. Various influences can lead to an increase in the spread of the values. This can be seen on the far right of the diagram. There, the spread of the values has increased so much that 3 values are outside the permissible specification. Because increasing process variation can lead to out-of-specification characteristics or products, the process spread should be monitored. Let's briefly review the meaning of the symbols in the formulas. Sigma is the standard deviation of the population, and sigma hat is the sample standard deviation. The B factors are required to calculate the warning and control limits. These are taken from tables. These factors are calculated using the chi-square distribution, depending on the size of the sample and the non-interference probability. There is a separate lesson for calculating these B factors. To calculate the limits, the standard deviation sigma of the population must be known. Since this is usually not known, it must be estimated as best as possible using a random sample. This random sample can be taken from an ongoing series production or from a pre-series. In this chapter, let's take a look at the result of such a pre-series and use the measurement results to calculate the standard deviation. Several random samples were taken and the diameter of each part measured and the measurement result entered in the table. Then the results were entered into the control chart. This resulted in the value curve shown here. When calculating the warning and control limits, it is assumed that the values are approximately normally distributed. A visualization in the histogram and the envelope curve above it should be sufficient proof of this at this point. The standard deviation was calculated for each of the 5 individual values in a sample and written in the right-hand column. The mean value was again calculated from these standard deviations. The value S bar is 0.028 mm. This is the center line of the control chart. The standard deviation of all individual values must now be calculated based on the same measured values. This can be done, for example, with MS Excel and the function stdev.s. However, there are other methods that can be used to estimate the standard deviation. 2 of these are shown on the right. If you don't have a computer to help you, you can also calculate the standard deviation manually using the range R and the value dn. Values for dn and an would then have to be taken from tables again. Now we come to the actual creation of the control chart with its 95% warning limits and the 99% control limits. The structure of a standard deviation chart is like that of the other control charts. On the y-axis, however, is the scaling of the standard deviation. In the table for the measured values, the standard deviation is calculated from the values of a random sample and entered in the standard deviation chart. The warning and control limits are also calculated for the usual 95% and 99% non-interference probabilities. In the first chapter, we calculated the standard deviation for all 50 measured values using the MS Excel function stdev.s and rounded the result to 0.03 mm. As has already been said several times, values for the B factors are taken from tables as they can be found in the relevant literature or on the internet. A small excerpt of such a table is reproduced on the left. For the sample size of 5 given in this example, we can now take the values for the B factors from this table. We now have everything we need to calculate the warning and control limits. Next, the values are inserted into the formulas and the limits of the control charts are calculated. The upper control limit is 0.058 mm and the upper warning limit is 0.05 mm. Both were plotted on the control chart. The lower warning and control limit is only 0.01 or 0.001 mm. Since one strives to reduce the spread anyway, it actually makes no sense to draw lower limits so close to zero on the control chart. Therefore, in such a case, they are simply omitted and are only indicated here. Here is a brief explanation of what these limits mean. The warning limits UWL and LWL are such that the standard deviation of a sample will lie between these limits with a probability of 95%. For the control limits, this probability is 99%. For the reasons just explained, the lower limits have been removed in this control chart. The probability that the standard deviation of a sample exceeds the upper control limit is less than 1%. When such a rare event occurs, it is an indication that the process may be out of control. The cause must be identified and the process readjusted, if necessary, in order to reduce the spread again. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 3 most important key messages. The standard deviation is a measure of the spread of the values of a characteristic around its mean value. An increasing spread, that is the standard deviation, can lead to out-of-specification parts, which is why this must be monitored. The probability of non-interference in the process is 99%. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye!